Hello, and welcome to Pulumi TV. My name is Mike Metral. In this installment, we'll review how to use RBAC for Kubernetes apps. Specifically, how do we associate an identity with a given pod launched in a Helm chart? Let's begin. On a general level, assigning identity to workloads is pretty straightforward. You have two general steps. You consume the role with the policies that you need, and then you consume that through the service account in a pod. But what is a service account? In Kubernetes, a service account is an identity for a given pod and the processes running within that pod. It allows the cluster to identify who in fact is running this and with what permissions. As you can imagine, working with pods in a Kubernetes cluster will vary at this step when it comes to identity, whether it be on AWS, GCP, Azure, or on-prem. The implementation details will ultimately fall on the provider enacting the identity piece in this equation. Let's dive deeper into what this looks like in AWS. As we can see, there are a couple more steps to what actually takes place behind the scenes. When we have a given pod and a service account for that pod, the first step we have to do is create a given role with a particular STS action. The Secure Token Service by AWS has created a particular action that allows us to readily identify the service account within the context of the Kubernetes cluster and within the context of IAM in AWS. This role will hold the permissions that we ultimately need. In our example, we're going to review how to actually stand up FluentD CloudWatch through a Helm chart by leveraging per-pod identity. After we've created the role with the necessary permissions to be able to work with CloudWatch, we're going to get the role's ARN back. This ARN is annotated on the service account because this is the first foray into how we eventually will get tokens with the proper permissions. After we've annotated the service account and the pod comes up and it's runtime, as you can imagine, the pod will have to communicate with CloudWatch. How does it do that? Well, given the annotated service account, the next step actually is for the pod to communicate with an OIDC provider that is attached to the Kubernetes cluster. This OIDC provider allows us to leverage the OpenID components that the clusters in Kubernetes support and that AWS integrates with. So when we leverage this service account at the pod's runtime, what we're actually doing is that we're authenticating with the OIDC provider that's attached to our cluster. That provider will return a temporary token for us to then follow along with. On instantiation, as soon as the pod needs to communicate with CloudWatch, it'll swap that OIDC token for an STS role cred that is temporarily given to it on a timely basis. These creds are then passed along to EKS, the service, which then in charge leverages a dynamic webhook that mounts these temporary STS creds as a token into the service account that our pod will ultimately leverage. Once this is mounted into the service account, the pod has everything it needs to communicate with the service, which leads to our last and final step to use the actual service. A couple of references are here for you to review. The code that we're going to dive into now is available at our Pulumi TV repo, and there's a couple of links for you to follow along in case you want to implement this on AWS, GCP, or Azure. The general flow, however, will be similar from cloud provider to cloud provider. Implementation details are where they're going to differ. So let's visit how this looks like in AWS. If we jump over to our text fields over here in our terminal, this is the basic definition for how we instantiate a cluster on AWS using EKS. Pulumi allows us to leverage various Kubernetes components, whether that be components that are created for configuring EKS clusters, for deploying workloads into clusters, or for manipulating Pulumi as we see fit. We'll stand up an EKS cluster in a couple of lines of code, and specifically, we're going to enable that we create an OIDC provider, as this is not the default for EKS clusters. This OIDC provider will ultimately be attached to the cluster as we see in the image on the left. After the cluster has successfully come up, we'll expose its kubeconfig file to leverage deployment of resources into the cluster, and then we'll actually leverage the OIDC provider's URL to tie the pieces together. As we mentioned earlier, let's see how this looks like to deploy a Fluentd CloudWatch Helm chart using pod IAM. We'll comment out this code as we've done the work already to actually make sure this is a running example. As you can see, because I have a language at my disposal, in this case TypeScript, I have the full capabilities of a language to leverage. That is, creating new classes, leveraging functions, having the ability to jump into documentation, being able to have my omni-completion tell me when I inadvertently type a property that does not exist, or if I have a typo in my definition, we are notified by our editor and the TS server of what must be done to correct this. Off to the races already, right? Programming languages allow us to work better with our infrastructure, with our Kubernetes clusters, and for the workloads that go into those clusters. As you may have caught wind, right here, what we have is a custom component that we've created called Fluentd CloudWatch that requires a couple of parameters. The cluster, and more importantly, the kubeconfig file to talk to the cluster, the namespace in which we will deploy the Helm chart, and the OIDC provider's ARN and URL that we will need to configure the pod's identity through the service account. Let's jump into what this component actually looks like. Here we have a custom component resource that we've decided is the proper level of abstraction for our use. You could easily create components of your own. You can create libraries that expose functions if you choose to do that instead. Or you can simply export ID values if you are the one in charge of provisioning the infrastructure and your colleagues are the ones in charge of just consuming that. How you divvy this up is going to depend on how your teams operate, how your organizations are operated, and more importantly, how roles and responsibilities are divvied up in the cloud provider of your choice. If we dive deeper into the code, there's a couple of generic steps that we have to follow to actually provision the Helm chart, which we'll get to in just a second. As we mentioned earlier, the Helm chart will launch a pod for Fluentd, but it's going to leverage a service account that provides an identity within the cluster and that's attached to identity within AWS to actually be able to communicate with CloudWatch. This service account is going to be bound to a certain set of roles in the cluster. And last but not least, we're going to create a new log group in CloudWatch using the Pulumi AWS library in a single line of code. This log group will be passed on to our create Fluentd constructor, function, that will actually deploy the Helm chart for us. Let's look at what the Helm chart looks like. Pulumi allows us the ability to instantiate many resources, Helm charts, YAML files, and even direct support for the API resources in Kubernetes such as deployments, secrets, config maps, services, etc. In this case, I wanted to grab a Helm chart off the shelf of Fluentd CloudWatch. Doing so is as simple as defining a new resource for Helm that takes in the namespace that will be deployed into, the name of the chart that we're pulling from the given repo, in this case, is the incubator, the version of the chart that we want to leverage, and some custom value templating as you would normally do in Helm by editing the values.yaml file. In this case, we are doing a couple of necessary steps. We are providing some configuration that Fluentd needs. We are establishing that the region that we're in is ultimately going to be provided to us by the ambient color given to us in a simple helper method called aws.getRegin, which leverages the Pulumi AWS library. Next, it'll forward and aggregate all of the logs and store it in the log group that we created. And last but not least, we are going to leverage a service account that we created above. And this part is important. As we mentioned earlier, there's two levels of RBAC. At the cluster level to authenticate access into the cluster, and then within the cluster to allow it to do certain sort of permissions within the cluster and any services that it may operate, such as CloudWatch. Because it's a Helm chart, a lot of the defaults have been taken care of for us, in this case with regards to RBAC of the application. So it'll stand up the proper RBAC resources that it needs, but we are specifically giving it the parameter of the service account that we want to use that we know has been authorized to work with the OIDC provider and, more importantly, CloudWatch to forward all logs to. This step, as far as creating the FluentD Helm chart, would be very similar to any instantiation of any Helm chart across AWS, GCP, Azure, or on-prem. This particular example will only work on AWS given that the chart is particular to CloudWatch on AWS. But the details here are analogous to running any other Helm chart that needs identity. You simply would spin up the Helm chart of your choice and pass it the service account that we created above and we'll jump into shortly that allows it to communicate with the identity permissions that it needs. Let's look at what creating the service account looks like. As we provision the Helm chart, the service account is going to require that we assume a particular policy that AWS has allowed us to consume to enable web applications of this kind. In other words, we are able to associate a temporary web identity that has been authorized by the OIDC provider to verify that the service account actually exists. And ultimately, this will be how we exchange the temporary OIDC token for a STS token in AWS with the proper permissions. This format is a default format that we require when working with AWS that actually binds it to the service account in question. In this case, we have to have a perfect match on the string equals that the service account is coming from this given namespace using this given name. This allows us to tie the identity particularly to the service account that the FluentD pod will in turn be running. The role, much like any other role in AWS, requires a couple of properties: a name and the policy that it must assume. In this case, it is the role with web identity that we've identified above. Once we've actually assumed the policy, we're going to attach additional policies for FluentD to proactively be able to work with CloudWatch. In this case, this is as little as attaching the given policies we have here that give us the actions to work with, read, update, and create new entries in our log group. If you're familiar working with identity in AWS IAM, these statements here should look very familiar to the JSON or YAML you're used to working with. The only difference is we are doing this in TypeScript, so we can programmatically edit it, reference it, and use it. And a perfect example of that is when we take the policy that we just defined up here to work with CloudWatch logs and attach it via reference to the role we created that assumes the necessary role with web identity that AWS requires. So, to summarize, we have to assume a default role policy if we want to exchange a OIDC credential for a STS credential. And then we have to do the added benefit of defining the permissions that your pod or application in this case will need. Once that is created, what we are going to do is take the given role that this function returns in this line and pass it to a new server's account that we're going to create that references that role's ARN. Let's jump into that method. Or function, rather. In this function, we are creating a standard Kubernetes service account. Once again, we are leveraging the Pulumi Kubernetes library here to create these resources that are first-class citizens in the Pulumi Kubernetes library. These look and feel just like the same YAML and JSON that you may be used to working with if you've worked with service accounts. The only difference is we're doing this in real language. For a service account to leverage the role that we just created, we are required to annotate it with a given prefixed key and then the role ARN as its value. This is ultimately how we are able to connect the dots between the service account and which permissions will ultimately be granted to it. In this step, the service account becomes created. We'll take the name of that service account by representing its metadata, and ultimately this service account will be what we provision in our Fluentd Helm chart when we specify the RBAC policy to use the service account in question listed here. So let's retrace our steps. We stood up an EKS cluster that has an OIDC provider attached to it. We're going to deploy a Fluentd CloudWatch Helm chart, which is configured to leverage the OIDC provider and URL that we must work with to get a OIDC token that in turn will eventually become an STS credential. We facilitate that through the ability to create a new role with the given permissions that we need, annotate a new service account with that role's ARN, and then at runtime, behind the scenes, when Fluentd consumes the service account, we're going to see the exchange that we have identified here on the left. So we created the role, we'll annotate the service account. When the pod runs and is ready to actually communicate with CloudWatch, it'll auth against our OIDC provider, get that token, swap it for an STS credential. STS will pass that along to the EKS service, which in turn has a dynamic webhook that the EKS control plane service automatically will mount into a service account token that our pod consumes. So steps 1 and 2 are the main ones that are required for us to describe the permissions that we need and associate those permissions to a given workload. Steps 3, 4, 5, 6 all happen in the background in the context of the OIDC provider being stood up, but more so that the IAM services and the OIDC provider will communicate for you given this construct that AWS has made available for us. So after we've created the role and annotated our service account with its ARN, transparently all these steps will happen. They'll issue us a temporary STS credential, and ultimately we'll actually be able to hit step 7 and use the CloudWatch service. Let's go ahead and launch this cluster and its workload on the right. We've taken the liberty of standing up the cluster for the sake of the demo, and we are now going to launch the Fluentd Helm chart using the properties we've defined on the left with the given role and service account. Let's run a Pulumi up. As we see, the Helm chart will begin to build out and create its pieces through the Pulumi engine. It'll tell us what we plan to actually create, if there's anything to remove, and if we want to actually execute this update. Let's say yes. Within a matter of seconds, this deployment will ultimately complete. Great, it's been stood up. If we look at our Pulumi output, we can see that we've exported the log group name that we'll be using to aggregate and push logs to within CloudWatch. Let's see what that looks like in CloudWatch. So if we take this log group name, jump over to CloudWatch, and look for this log group, we'll see an empty log group. This is because it'll take a couple of minutes for the pods to actually emit logs and for Fluentd to collect it. If we look at our cluster, and examine the pods within that cluster, we'll see that we have 2 copies of Fluentd as we have it running as a daemon set across both of our nodes. If we jump into the logs of that pod, we can examine a bunch of output from the std out of Fluentd showing its configuration and ultimately aggregating and pushing this off to CloudWatch. Let's refresh. This may take a couple of minutes as we are also succumbed to potential rate limiting if we happen to go past our initial usage. Aha, as you see, log streams are slowly starting to trickle in. Let's look at this one. This is exactly the same log that we've seen on the right that we were retrieving with kubectl. Except we have this in CloudWatch for us to examine, analyze, and centrally aggregate. Let's see if there's any other pods that have emitted logs. Not quite. Let's let that run for a sec while a couple of more show up. So to revisit, the only necessary steps we have to take are for us to define the role per the requirements to get STS credentials, attach the policies that we need to that given role, in this case, be able to work with CloudWatch, attach the two, and then associate that ARN with a given annotation on the server's account that will be consumed by the pod in question. In this case, a Fluentd Helm chart. Similarly, we can examine that all of this implementation detail outlined in the server's account, creation, the role creation, and the attachment is going to vary from cloud provider to cloud provider. But generally speaking, no matter the cloud that you're on, there's going to be some capability to create a server's account that is attached to the identity service of that platform. Here are a couple of links to get you started on other cloud providers if you so choose to try them out. Again, this approach is no different. The general stance is we have to create a given identity in the provider of our choice and then consume the identity through a service account. Hopefully this helps clear up how to leverage app RBAC, how to associate this with Helm charts, and more importantly, how to generalize this no matter the cloud that you're running on. And last but not least, once these logs are in CloudWatch, this allows you to analyze it, examine it, and inspect it as you see fit using the rest of the suite of services the cloud provider offers. This will continue to take a couple of minutes for us to see a full output of all the logs for all the pods that we have. But the premise is the same. There'll be an individual stream associated for each pod that gets output into the log group that we created, funneled by Fluentd, and facilitated by a server's account that leverages IAM permissions with least privilege, an OIDC provider, and the AWS STS service. That's all the time I have. Hopefully this was insightful. And here are the links in case you want to check out more. The code for this example is featured and found on Pulumi TV on GitHub. Feel free to drop us a note, share this, or open up any issues that you may have encountered in your experience. Thank you, and have a great day.